We're now going to take a look at elementary matrices and how they might be related to the inverse of an invertible matrix. Before that, however, I want to revisit a concept that we talked about earlier, and that concept was actually what our procedure for solving a linear system is built upon, in that when we perform these row operations, they don't change the system, right? In other words, they don't change the solution set to the linear system. And so just so recall, two matrices are row equivalent, right? And this is a word we used way back when. Two matrices are row equivalent if there exists a sequence of row operations that convert one to the other, right? So if there is a sequence of these elementary row operations that we can perform that will convert one matrix into the other, then we say that they are row equivalent, right? And again, this is a principle that our Gaussian elimination, Gauss-Jordan elimination is built on, that we can use these operations and not worry about affecting the solution set, right? So now we previously saw that with every row operation, we can associate that with an elementary matrix, and in fact, pre-multiplying by that elementary matrix will perform that same operation. So now we can rethink this concept. So instead of thinking of it purely in terms of just a sequence of operations, we can now think of it as a sequence of elementary matrices, right? So here's kind of a take two on the concept of row equivalence. So A and B are said to be row equivalent if there exists elementary matrices. So elementary matrices. So let's say E1, E2, dot, 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 E sub k, such that when I apply these elementary matrices in sequence to say A, at the end of applying all of these elementary matrices, I will have matrix B. Now remember, in terms of applying an elementary matrix, it's that pre-multiplication. So if I start with A, for instance, and then I apply this matrix E1, so it would look like this. It would be that product. And then after doing this product, I would then apply the second elementary matrix, which would be another product. So I'm going to kind of put it in parentheses to kind of show the order of operations. But all this basically is saying, if I take these elementary matrices and one at a time perform my pre-multiplication, right, of A with each of the E's, then eventually I will end up with B. So if I do this, and then maybe I'll do another one for emphasis, like that, so that'll be E3. And then dot, 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 all the way down to the very last one, E sub k, like that. And then again, so these are all matrices that are being multiplied in a particular order, and we know we can't really just switch the order of multiplication, because in general, matrix multiplication is not commutative. But at the end of that, we're going to end up with matrix B. So then this is going to be equal to B, right? So now instead of just saying, okay, yep, we perform some row operations in sequence that will convert A into B, we can be a lot more precise and say, okay, if I have my elementary matrices that are created by those same row operations, and now if I use them in my pre-multiplication, multiplying these all out will give me matrix B. Now, the parentheses are just being used for emphasis, but because of the associative property of matrices, I really don't need to indicate the order like this. In fact, if I write this, there is no ambiguity at all, right? If I just write this like, we normally write products like this, then that will be equal to B, right? So again, this is the equation that we work with to illustrate this concept of row equivalence. Now, why is this important? Well, now if we fast forward and think about what we've recently done with the inverse, the whole idea and the process behind finding the inverse of a square matrix, assuming it's invertible, is that we start with our matrix, we perform elementary row operations, and what do we get at the end? We get the identity matrix. So if A is row equivalent to the identity matrix, then A is invertible, right? Again, that's a recently discovered fact, right? So let's say this. So if A is row equivalent, not just to some random matrix B, but now specifically the n by n identity, right? A is invertible. Okay, so then let's translate this in our new format and just replace the B with the specific n by n identity. So let's write that down. So again, if our matrix is going to be invertible, right, then I would have to have a sequence of these elementary matrices that if I, again, multiply them, do my pre-multiplication in order, one after the other, then the end result is going to be the n by n identity. So, right, let's write that down. In fact, it's simply restating this equation, but now with a specific matrix in mind. Right, so we have this, and there is our IN. All right, good. So what does this mean? Well, look closely at it. Here we have this, if we were to, multiply out all these matrices, we would get a single matrix here. But look at what this equation is saying. This equation is saying what I have here, in fact, let me highlight this, or at least box it off in a different color here. What I have in blue, when I multiply A, produces the identity matrix. So that means what I have in blue has to be the inverse of A. So right away, we have like it's a formula, right? But it's now in terms of these elementary matrices. So this implies that E sub k times dot 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 E sub 3, E sub 2, E sub 1, that has to be the inverse of my original matrix. That's the only way I will get the identity here, right? So again, this is an important fact, and we're going to actually state it as a theorem, but what this is saying, the inverse can be expressed as a product of elementary matrices, right? So that in itself is really good. Now, let's go back to this original equation, right? Now, suppose, and we saw this in the previous video, that each elementary matrix has its own inverse. What is its inverse? Well, it's the elementary matrix that would undo whatever operation E does, right? So if E does, like say a row swap, its inverse would swap it back. If E does multiplying a row by a non-zero constant, then its inverse would be multiplying the same row by the reciprocal or with the reciprocal of that non-zero constant. So each of these E's will have an inverse, right? Why is that helpful? Okay, so I'm going to write this equation again, right? It's like we're seeing E's. But say let's look at this now, and this is another matrix equation. On this side we have the identity. Let's say I wanted to try to isolate matrix A, like I wanted to solve for A. Well, I could multiply both sides by the inverse of this, right? So then this looks like this. I'll put the dot 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 there because really there's going to be, after multiplying by E sub k, I'm going to be left with another elementary matrix there, and then that inverse would multiply this, so like times in, right? But we know multiplying a matrix by the identity gives us the same matrix. So on the right hand side, what we have is just E sub k inverse. So it looks like that, and then over here, yeah, I have there is now another elementary matrix at the start here, right? And then eventually I get to E3, E2, E1, and then times A. But then again, if I want to continue doing that, what I would have to do is multiply each time by the inverse of whatever elementary matrix is in front, right? The first factor here, multiply both sides by the inverse. And what I would have to end up doing, if I put the inverse of this matrix on the left on this side, then I have to put it on the left on this side. And if I continue that pattern, this is what will happen, right? So I'll just do dot, dot, dot. So A is going to be equal to, and let me write it like in reverse here. So first I will have E sub k to the negative 1. Then in front of that I will have E sub k minus 1 to the negative 1. And then dot, dot, dot until I get down to E sub 3 to the negative 1, and then times E sub 2 to the negative 1, and then finally E sub 1 to the negative 1. So these two equations, right, let me highlight them. They tell us something very important about an invertible matrix and its inverse, right? It's saying that the only way a matrix will have an inverse, right, is if either both the matrix A and its inverse A inverse can be expressed as a product of elementary matrices. So both the inverse and the original matrix can be expressed as a product of these elementary matrices. In fact, it actually gives us a way of factoring a matrix, because that's what we've done here. We've taken one matrix, right, both the inverse and the original matrix, and we're able to write it as a product of several other matrices. And that in itself is a huge thing, particularly in a field called numerical analysis, numerical methods. The idea of being able to factor a matrix is a big deal. And for invertible matrices, we have a natural way of doing it now by using these elementary matrices. So let's actually state that as a theorem, right? And yep, that big kind of theoretical leap forward. So here's our theorem, and it says A is invertible if and only if A, and then in parentheses I'll put and its inverse, right? So, and its inverse can be expressed as a product. And I'm not saying the product because there are different ways to do it. Because, for instance, what if we were to do our elementary row operations in a slightly different order? Then we would end up with a slightly different sequence of elementary matrices. So that's why we use the word a and not the, because it's not a unique product. So it can be expressed as a product of elementary matrices, right? And in fact, I'll just say this gives an important, so that's the end of the theorem, but I'll just add that particular note that I mentioned about matrix factorization. So I'll just put a note. This gives a systematic way of factoring invertible matrices, right? And again, it might not be entirely apparent why this is important, but we've seen, if you think about it, we've seen how important factoring is in the algebra of functions and numbers, right? So it's not a huge stretch of the imagination to think that, yeah, factoring is going to be important in the algebra of matrices, right? Particularly the invertible ones. And as I said, those of you who will be going on to take courses in, let's say, numerical methods, numerical analysis, you'll see exactly how these factoring procedures affect certain algorithms that are extremely important, right? So this was a kind of a theoretical uh, video. Hopefully you followed, and it you know, we're now seeing the connections between different aspects of the course. In the next video, I'll actually do an example to illustrate, okay, how do we find this factorization? What does it really look like, right? But I wanted this video to be exclusively just introducing the idea, and then as a result of these ideas, coming up with this particular theorem. So if you hop on over to the next video, you'll see an example or illustration of this theorem. See you then.